it will, I think I might do 2 files for this class. So each class will have 2 files. The name might be, you know, the name might be weird, but we'll have to deal with that one as we go along. So, but anyway, as I was saying, I still have to change the syllabus. I will update the syllabus. I'm probably going to have you watch some space-time videos or something like that, or assign a few, and or NASA missions, and have you write a short paper on it, because group projects aren't really going to work. And so I'll cover the planets, but I'll cover them briefly, so that way everything works. I delayed everything, so ideally your first quiz would have been assigned this week, and I'm still going to do that, but I won't have it due for a little bit. I'll have the first one probably due next week, and then we'll go forth from there, because we need to be sure we cover eclipses before I assign the first quiz. So the instructional break sort of threw us all off. And I'll update the syllabus because I noticed we only have about half of you here, so which is fine, but you know, I also have to assume that people have trouble. That's why I'm putting the lectures online. So so we are going to experiment with a few things. So it'll be a little clunky going at first, but I think we'll get there. So is everyone ready? I'm going to start. Any questions before I start?
Hear me?
No? Okay. So last time, when we went over the syllabus, you know, the very first time we met, because the semester started on a weird day, we spent our time looking at the scales of the universe. We saw our powers of 10 video, and we also saw, we also really looked into what we can observe, what we can see. And I want to review a little bit of that first. I don't want to do it in too much detail because we do have to get going, but it's stuff that should make some sense. So again, the first means of observation are your eyes and your ears and your senses. Now, because everything in astronomy is very far away, can't really touch it, can't hear it, can't taste it, certainly. So you have your eyes. The eyes are the main apparatus in which to make observations. So you'll notice we talked about what we could see. I got to get my pointer going here. What we can see is the night sky. We have our stars and our Milky Way, right? And as we look, we found patterns in the sky. As I told you last time, I'm not very good at recognizing patterns or seeing them. I mean, I kind of see Orion, but I think I've forced myself to do it. And of course, the Big Dipper, but you know, the rest of this doesn't look like a snake to me in particular. It just looks like an attempt. So you know, we have our constellations, and it's important to note that the human mind is sort of optimized to recognize patterns, which is why we see constellations. We try to find patterns everywhere we go. And this is important for things like when you can recognize a dangerous situation versus a non-dangerous situation. These things are important for survival, right? Because we haven't always been on top of the food chain. So we want to go and see what we have next. From what we can see, we introduced the galaxy. We can only see this fraction of the galaxy. If you'll remember, mostly dust and blocks out and scatters the light. We're going to talk about light interacting with matter. We're going to spend a lot of time before we get to astronomy. And I don't know if I said it last week, but in this course, it's going to feel really dense. Not starting sort of at the end of this chapter or the end of this week. Next week and the week after, you might wonder, what the world am I doing here? It's going to seem a little hard as we're going to get a little technical. We're going to talk about math. Again, we're not going to do a lot of it. But what's important to understand there is that we need to build up the vocabulary to understand how things work in astronomy. Because remember that? Does anyone remember that one question I asked? You should always ask me. I'll wait for typing or you know, chiming in. Does anyone remember? It's been a while, so it's okay. Well, the question you should always ask me is, how do we know something, right? If I tell you the universe is 13.7 billion years old, how do we know that? If I tell you galaxies are moving farther away from us, the farther they are away, how do we know that? If I tell you what star, what elements are in a star, what stars are made out of, you should be able to ask me, how do we know that? And I should be able to explain it to you. I've not figured out how to turn off the email notices, so whatever, I'll get that later. Usually I can just ignore them. I'm not talking from home. But anyway, but that's the key to our class, right? I want you to gain an understanding of how we know the things we know. And the answer to a lot of that is understanding the basic physics, how light interacts with matter, and how physics works, the quantities we use to define motion. So again, we only see a limited fraction of the Milky Way because of how light interacts with matter in the spectrum that we see it, okay? And we'll talk about the observations that lead to our understanding of us living in a beautiful spiral galaxy later. But again, keep in mind the scales. It's like I said, it has been a while. So if you look at the scales here, does anyone remember how much of the night sky fits into this dot? Anyone want to take a guess? That's all right. Take a guess. Just shoot it out there. It's okay. 50% of the night sky, 100% of the night sky. All right. Good guess. Oh, well, it's good. Anyone who was absent the first day should let me know, because I have to do a certain type of attendance, so this counts as showing up. But take a guess, Angelica. That's fine. You can, there's this class is meant for guessing and not knowing. There's no issue here. We're all here to learn. 75. Okay, good. So actually, everything we see would probably not cover a pixel or night sky. So this very much this yellow dot over-represents stars in the night sky. We can only see about 2,000 stars with our naked eye. With this probably will cover what you could see with the telescope, a good telescope. You're able to see the whole night sky. And remember that even though there are, 2,000 stars that we can see in the night sky, our galaxy harbors anywhere between 100 and 300 billion stars. I did not say that wrong. I didn't mix that up. I know sometimes people mix up million and billion. But there's hundreds of billions of stars in this structure, and our sun is just one. So, I think for Angelica and others who are absent, or were absent, you might want to check out the Powers of 10 video from the 70s on YouTube during break or at some point to get an idea of the scales we talked about last week. So I'll be referring to that frequently. Okay, so moving onward and forward. We talked about how we talked about this. Remember, this is reviewing. So for those of you freaking out, we talked about how we look at this stuff. And again, the math will be, if you're worried, oh my God, he's not going over the math. All we looked at from here, for instance, to remind you, is how we got to minutes and seconds and use the base 60 time scale for time. You can thank the Babylonians for that. Thanks, Babylonians. And we look at the we understand the sky in terms of spheres. All right. So, but we're not going to focus on that. Well, we want to focus on the things we observed. So let's get to the sky as it orbits. We talked about the length of the day and the Earth's rotation, and we talked about the seasons. Does anyone remember? This is complete review. We did this last time. So true or false? Earth is closer to the sun in summer and farther from the sun in the winter. False. Good. Good. I like seeing all those falses. In fact, the question, if you want to be, if you can imagine a young Professor Toland being really annoying in high school, I would have looked at this and said this is an ill-formed question because, and the reason it's ill-formed is the reason it's the intention behind its ridiculousness, which is that it's never either summer or winter on Earth. It is summer in the northern hemisphere,
Wait, I have a
winter in
question.
oh yeah, did you raise your hand?
I forgot what was the name of the video that you said to look up on YouTube?
Powers of 10, 70s. You'll see it. Yeah.
Okay, thank you.
Yeah, and just click the thing because I should get a ding. I didn't hear the ding, so just give it a try. It's right by the video thing on the bottom of the chat session. It says raise hand.
Oh, the little wave thingy? Okay.
Yeah. If you do that, then I'll hear you, and I won't keep going. I promise.
Okay, got it.
Okay? Wonderful. So it's false, but what I would say is that that because we have seasons depend on what hemisphere you're on, you can't say the Earth it's always summer or winter somewhere. So it doesn't matter. But what's interesting is the Earth actually is slightly closer to the sun in the northern hemisphere winter, or what we would call winter. So false is right, and as you can see, it's the tilt of the Earth that that affects the sun. Now, I want to try something. I'm not sure this is going to work, but let's give it a shot. Things might go caca, so be prepared for some crashing. So I'm going to load up the. I can't run the simulation like it is. Oh, that's why that's not working. Okay. All right, so I'm going to play the simulation. Hold on. Oh. Okay. Everyone's talking. Blah, 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 blah. Hold on. All right. This may not go well. Slideshow. Hold on. All right. Everyone still there? Okay, good. Because it's all right. It's getting let me see here. New cosmic astronomy. All right. It's not. Hold on. Let me reload this. It is not working with me here. Huh. Oh, no, that was bad. Hold on. Okay, we're going to go back here. Okay. So basically, I'm going to have to improvise this a little because I can't play it. Or at least I forgot about all the flash. Me too. me too. I missed the physical classes too. So if you can see, if the Earth is spinning, let's see. I have a. Give me 1 second. Hold on. I've got an idea. Hold on. I just saw that thing. Here we go. Okay. Always got to find something. You're about to start video sharing. Oh, wow. Okay, does everyone see the sphere here? So if you imagine it's on an axis, you can see it might be a little hard to see. Let me turn on my light. Okay. If you can sort of see it's at an angle, if the sun is shining, like on the Earth in the shared picture here, all right, you'll notice the light hits more of this northern hemisphere here. You'll notice the light when you look at it from this picture is tilted. It doesn't make a half hemisphere. If there were no tilt, every part of the Earth would get the same amount of light, half and half, every day. All right, but because of the tilt during what we call summer, the northern hemisphere sees more light, and you'll notice it does not get light, or it gets light. It doesn't get dark at the North Pole as the Earth spins. And then this whole thing reverses when the Earth is on the other side, because on the other side the light is still coming from this way, right? But now with the tilt has changed the other way. It's illuminating the southern hemisphere. So that's not as good as I'd hoped, but because we have sort of a meridian and everything. But if you can sort of see the idea there, that you'd have an axis and a sphere. I'll put the axis here in front of the camera. That would work. You know, and different amounts of light will hit it at different times. I'm going to have to figure out that thing by next week. Or I might do it during our first break, actually. See what I can figure out. So the result of this is that the sun stays at different places, or what you're seeing here is a picture of the sun at the same time throughout the year. And you'll notice during the summer, the sun's higher altitude means more direct sunlight, and during the winter, the sun's lower altitude means less direct sunlight. So I don't want to get caught up too long on the review, even though we should have seen that stuff. So we see that the axis tilt is the reason for the seasons, but we need to talk about the seasons because the seasons will give us reason to predict things, specifically a flood or wet season versus a dry season. That's going to be that is important for things like growing crops and farming. Distance doesn't matter so much because the Earth's orbit is nearly circular around the sun. It is elliptical, but it's very, very nearly circular. Mars's orbit, for example, is not. It's much more elliptical, and the distance actually matters. The tilt matters quite a bit too, but you have sort of a compound effect where one hemisphere has much harsher seasons than the other one. So we'll see that when we talk about Mars. Now, we're getting sort of towards the end of where we did before. This is a 24-hour day. I remember when I was a kid, I was always fascinated with these whole this idea of it not getting dark. And I remember wondering what the sun did, and I didn't think about it for a long time. But then this slide gives you an idea that if you're at the North Pole, you see the sun sort of set, but then it doesn't quite make it, and it just rises in the sky again. It would be pretty cool to see, I think. That would be pretty awesome. But you can see here there's a cutout of 24 hours, and you get the whole day. So this is the path of the sun on the summer solstice at the Arctic Circle. So that's pretty cool. Other things we see, we talked about the Earth's precession rate, the North Star not being the North Star. We sort of ended talking about the moon and the phases of the moon. Now, you'll notice with the moon, I remember asking this, so I know we covered it, that it doesn't always look the same, right? It's not always in the, my camera hasn't decided whether there's one of me, two of me yet, so hopefully it'll fix itself in a little bit. But with the moon looks different as we see it. We pointed that out. So what's going on with the moon? Well, with the moon, we see different phases because of how the moon rotates around the sun, and now I need to use their part of it here. All right. So we only see the reasons we see the moon the way we do is because the moon's year, or the time it takes to rotate around this big circle, is the same time to rotate around Earth is the same time it rotates on its axis. So essentially, a way of understanding this is that the moon's day is as long as the moon's year, right? With the year being what we call a month, because it takes 28 days for the moon to go all the way around like this. And then if you're looking at the moon as this person, it takes the same 28 days to make one rotation to turn around, right? If you just held this person in place without moving them, and they spun around like this, hold on, and they spun around like this, that's the other motion, okay? Usually in the class I get people up and demonstrate this, but I don't really even have enough room in my office to do that. So, so that's what we have going on here. I need to turn the sound off because that's going to be obnoxious. All right, I'll just turn the volume down. Okay. All right. I'll come back later. So basically, because of that, and the sun stays in the same. So if you can imagine here where the arrow is, a big yellow sun. Those rays of light, hold on. Actually, you know what? You don't have to imagine. There is an advantage here. Let me see. Hold on. So if you can imagine a big sun here that I'm drawing, right? With its rays. You can see this on here. So the sun will always stay right where it is on the slide. Even with the person moving around in a circle, right? And rotating as they move around. Now, if the sun stays stationary, let's draw some rays of light going forward. So the rays of light for the sun will always look like this. Now, I want you to notice something. If you're Earth, you only see the girl's face as she rotates around. So in this particular configuration right here, you can, the girl's face is facing towards the Earth, but you'll notice the sun. I did this backwards because she's illuminated here and not illuminated here. But the point is that if all the light is on this side of the girl, you can't see her. This would be a new moon in the way we've drawn it. As you go here, you'll get only half the light, right? This would be a half moon. Half the light is illuminated, and there's an angle. And then as we get over here, this would be full illumination. So that would be a full moon. Then we first wax, then we wane, and we get that half moon here, and then we get back to a new moon, and the cycle continues. Now, keep this in mind here. I want to go back. You'll notice the same, crap, there it is. You'll notice the same cycle here. All right, first we have the new moon. There's the sun, right? The sun is illuminating the part of this moon we don't see. So we wouldn't see a moon, we just see nothing. And then as we start to wax, right, the fraction of the moon we see gets bigger until we're at that point here where we see half the moon, first quarter. And then, again, it's a half moon, but it's the first quarter because it's the first quarter of the cycle, right? You get the waxing gibbose, which means you start to get more. You have the full moon, which is the halfway point, right? Because remember, the cycle is from the new moon to the new moon. So it's a little confusing because the half moon, the waxing half moon, is at the first quarter, and the waning half moon is in the third quarter. So, this is what I mean. You just sort of have to, it's just important to sort of keep track of it all, right? Don't worry too much about it. But again, you'll notice here, I want to point out the full moon, that what we call the dark side of the moon now is not being illuminated. And you just have to imagine that this girl can rotate and turn around, and she can see the full face that's being illuminated by the sun. Okay? And then as we get around, we get back to our new moon. Okay? So that's the basics of why the moon looks different and how we see it. And what's important to see here is that it's based on understanding how light works. Well, not how light works, but how light travels, right? We have a source of light that we know of, the sun. We have a body, the moon, and we can model it going around the Earth. And I'll remind you that one of our big goals today is to learn about the geocentric model of the Earth. And I sort of teased you last time, well, not teased you, but teased to the point of that the geocentric model is a valid scientific theory. It's an incorrect scientific theory. But what's important is not so much being able to identify correct and incorrect scientific theories. That's not our goal. Our goal is to understand why a scientific theory can be incorrect, how you overturn evidence and accept a new paradigm. And going from the Earth at the center of the solar system to the sun at the solar system, at the center of the solar system, and then having an expanding picture of the universe is kind of a practice in doing this constantly. Okay, so let us go forward, onward and upward. Are there any questions about the moon? Okay, don't feel bad. Just chime in if you've got one. But if you're good, then we can go. Okay, there's a no star. I don't know what the no star. Maybe there is. Don't be shy about them. All right, so let's go. Let's see here. Now, what we want to talk about now are some of the rare events we see, which are eclipses. I agree too. I mean, I enjoy not commuting, but it's missing a lot. It's missing a lot. I would rather be there, I think. No, I would rather be there. But health is important, and we don't really want to endanger anyone's health at this point. And as I don't know if you guys have been following the numbers, but New York would be probably 8th or 9th if it were its own country in corona cases. So, we're in the middle of it. And you add in New Jersey there. New Jersey and New York are kind of the same. So, anyway, we want to look at eclipses. Hold on, let me get my pen cursor here. And so you'll notice we have here that eclipses occur when the sun, and the moon, when the sun, the moon I think is supposed to be over here, and you know what? We're gonna go to the whiteboard here. This is making me angry. We'll come back to this picture in a minute, but I want to share a blank whiteboard. So let me write here. So we have the sun. Hold on. The sun, the earth, and the moon. All right, so we'll do it twice here. The sun, the earth, and the moon. Okay, now eclipses happen when you get an alignment between these objects. All right, and you'll notice that in this case, the top case, we have what's called a solar eclipse. Oh, you know what? I'll just type it in. That'll be nice. Hold on, because my handwriting is awful. So this is a solar eclipse. And, oh, right. And this will be called a lunar eclipse. And we'll label all of our stuff here. We'll call this the sun, earth, think I can fit it inside here, and the moon. So different things happen in these eclipses. So you'll notice for the lunar eclipse, the Earth will overshadow, this occurs during a full moon, and the Earth will block the sun's path of light to the moon. Now this is interesting, and we'll see pictures of this, because what happens is that the moon's shadow is reflected back onto the Earth, and the moon looks red. And the bonus question for today is, why do we see red? The more spectacular of the eclipses is the solar eclipse. So the solar eclipse happens when the moon blocks out the light coming from the sun. And we're lucky because we live in a time where this can happen, where the angular sizes of the moon and the sun, or of the moon, is slightly bigger than that of the sun, which means that it can go in front of it. Now, sometimes it depends on the distance. We're sort of at this place where we're going to be losing our total solar eclipses. If the angular size of the moon is greater than the sun, you get what's called a total eclipse. If you're high up, or if it's aligned so that the sun's angular size is greater than the moon's, you get what you call an annular eclipse. So the moon is still blocking the sun, but the sun is able to outshine it and have and see it. We'll always have annular eclipses, but total eclipses will, in a couple million years, be impossible. So if you can see one, there will be one in 2024. You should see it. We'll get back to the slides, because this will make a little more sense there. So let me go down to sharing the file. Okay. The scrolling in this program is not super great. So just give me a second, because I don't want to go through everything. It's not as easy as it is. It's not as easy as it is in other things. So if we look here, if we look here, we can see that we can see the shadow structure. So when you have the alignment, you have this umbra and penumbra shadow, this sort of inner and outer shadow, and you can see how the light aligns. So if the moon were right here, you can sort of see for both of these. So for the lunar eclipse, if the moon is over here, right, you'll see this whole shadow reflected back onto the Earth at night. And solar eclipses, you'll notice, only happen during new moons and during the day, for they would have to block out the sun. So let's take a look at the lunar eclipse, what it looks like. So you'll notice as you get into that penumbral shadow, you get this red color to the moon. And without it, you have this mostly this, and the reason for this is the sources of light that are reflecting off of the moon. So during the lunar eclipse, and during most of the time when we see the moon, we see the sun's light reflecting off the moon and down to Earth. So so the moon will look blue because that's the same color that scatters off the off the sky. However, you can only scatter once. Once you scatter, you can't reconstitute and reform. So you'll notice that you get, when you're in this penumbra, or in the, through the umbra, I messed it up. When you're through the umbra, you'll notice that the moon starts to look red, but you'll notice that you've blocked the sun as a source of light for the moon. And the only source of light to reflect off the moon is the Earth. Now, we're not used to thinking of ourselves as a source of light, but there's plenty of light constantly emitting from the Earth that we can see, that's being reflected from the sun or whatnot. And you'll notice that it looks red for a simple reason. I don't know if anyone wants to guess at the reason. That can be kind of fun. But the reason for the the red color, some people think it's pollution. Pollution might have a little bit, might affect slightly the type of red, but that's not really the reason. The reason is that the moon looks red here is the same reason the sky looks blue. If you look at the Earth as that sunlight comes into the Earth, all right, we see the sky as blue because that light scatters, and blue light scatters more heavily than the other colors. And your eyes are very sensitive to color, so the intensity will lock on the blue and shut everything out. However, if light is coming back up onto the moon from the Earth, that light has to be scattered first, right? And then only light that's not scattered can go, let me see here. Say my tip is the moon. Only light that's not scattered, I want to be sure you can see the, only light that's not scattered can go to the tip and reflect back to the Earth. And that is red light that does that. Red light does not scatter in the atmosphere. So it will reflect and go through and come back. So what you're seeing here is the shadow that the Earth casts on the moon. So that is pretty interesting. All right, and that's where that red color comes from. Now, eclipses were often seen, or were often thought to, you know, they didn't happen regularly. They seemed they at first seemed unpredictable. And strangely, one of the first things or signs of advanced development in astronomy was not just predicting, you know, regular events, but predicting these eclipses. And in fact, throughout human civilizations all over the planet, it seems that, you know, from the Aztecs to the Europeans to ancient Chinese and Japanese cultures and Aboriginal cultures and South Pacific cultures, there seem to be ways of measuring eclipses or predicting when they'll happen. Of course, this got more sophisticated, and we could predict them far in advance, but there seem to be attempts to do this all throughout human history. And you'll notice the solar eclipse, this is what I mean about it being spectacular. We had one pass through the United States in 2017, and there's one that's going to be passing through in 2024. Now you will be able to go up to, say, Buffalo and see the total eclipse. However, if you look outside your windows right now, it's supposed to happen in April of 2024. You can see why I'm not going to Buffalo and why I will go to Texas. If you look at the weather reports of both places, I'm guessing that it's a higher probability of non-overcast in Texas than in than in New York. And I, for one, will be, you know, I'm gonna make a barbecue and eclipse trip. So, but if you remember, you had those special glasses and special filters which will allow you to see the sun, and you can see the phases of the sun, or the phases. You can see the sun losing, being covered by the moon, and you'll notice in this area of totality, everything changes. And it's really weird. When I went to see the eclipse, the only way I could describe it is as eclipse. It's really not day, but it's really not night, and it's really weird. So I went to Missouri to see the total eclipse. It was pretty awesome, and it was spectacular. And you get this here. You get to see this layer of the sun that is not visible, generally called the corona, and this is the sun's atmosphere. And if you have a really good, if it's really covered well, right, you can see this thing actually extend way out to here. All right, and it's definitely different than the sun itself. It's dim but light. It's weird. It's pretty cool. But you'll notice that solar eclipses are narrower over a much narrower range than lunar eclipses. So if you had a lunar eclipse, basically lunar eclipses are visible from like quarter hemispheres. Like almost everyone can see them when they happen, and they happen a couple times a year. But this path length is even still too large. The path of totality for a solar eclipse is only about 15 miles long. That's not much. Or for my metric students, it's about 25 to 32 kilometers long. I'm just guessing at the thing. So you can see the path of the 2017 eclipse. It went right through Missouri. and then went down. You could have seen it in South Carolina, and you'll notice that in April 8th, 2024, we are we have that. That's the one I'm talking about. So you'll notice you can see it here in New York, but Professor Tolan's going down to Texas to get some barbecue. It'll actually pass right over Mexico City, which would be pretty spectacular. But I don't want to travel that far. You know, it needs a lot more planning. So let's take a look at some of the specifics of eclipses, because we don't want them to be. We want to understand a little bit why they happen. So if you look here at these pictures, you can see the moon. I'm sorry, I always mess this up. You can see the moon going around the Earth, but you can also see the Earth going around the sun, which gives you some perspective. And you'll notice that the new moon is the only time that you have a solar eclipse. It's the only time it's possible, and the full moon is the only time a lunar eclipse is possible. All right. So, but now what we want to understand is why these things happen. Well, the moon's orbit is actually tilted about 5 degrees from the orbital plane. That's this plane here of the Earth going around the sun. So that means the moon goes up and down. This is why we don't have 12 of these things every year. So we only have eclipses. So in order to have eclipses, we have to have a full moon and a new moon as we cross the orbital plane. Okay? Those are the only times that they occur. Most of the other time, it's all out of sync. So if we did have these things, if we did have the moon in the orbital plane of the Earth orbiting the sun, we would have a lot more eclipses, which might be fun. But that's not the case. So we don't have it. So questions about eclipses? As you say, the in-person class is better, so you don't get to see me. I don't talk so much and move. And I want to make sure we're okay. We're doing okay. We're on track. But like I said, I think what we'll do for those of you, I guess 10. I think what we're going to do is we will we'll just take a lot. We'll sort of do 2 90-minute sessions, and we'll take a long break, or 2 80-minute sessions rather. So even though we're not going to take a break in 10 minutes, we're just going to take a long one so that you can like do whatever you want to do, and then we'll come back and keep talking. So we'll give that a try. So anyway, I think everything looks good on eclipses. Let's go onward and upwards. Okay, so now other things that were observed. Now, I want to get to and set up this idea of a geocentric model. Now, I'd love to see a show of hands. You can just click by the thing. You know, just click the hand, the raise the hand button, and then let it go. You don't have to do it. But by show of hands, oh, Jose, did you have a question? I haven't gotten to my thing yet. Or are you just doing it? Okay, but by show of hands, how many of you know what the geocentric and solar-centric models are of the solar system? I mentioned it before, but coming into the class, you should know. So I've got 1. Okay, put the hands down really quick unless you have the question, because you just have to click it twice. So like, you know, once and then twice, so that I just know that you have it. Okay, so 1 or 2 of you, that's okay. So it's not so much of a big deal anymore, but there used to be this idea that somehow the idea that the Earth was at the center of the universe comes from divinity or religion, Eastern or Western, take your pick, and that the sun at the center is not. This is not quite a true story. It's one of these ones that will become simple probably in 200 years, such as it's like one story that you've learned that is absolutely not true is that they thought the world was flat when Columbus did his voyage, and that the Queen of Spain and that Columbus sailed to prove the Earth was round. This is not true. We're going to see in a little bit that scientists and scholars have known the Earth is round for about 2,500 years. So that's actually, not only did they know that it was round, they knew how big the circumference of the Earth was. They didn't know there were 2 other continents, that's for sure. Did not know that, but they were trying to find a faster route to India, so that you could avoid the spice roads and things like that. But what I want to convince you of is that it's similarly here with our Earth-centric and solar-centric models, is that the solar-centric model is based on observation, or the Earth-centric model, geocentric model is based on observation. And I think I can convince you that you would be a geocentrist with the observational data between you. So I want you to think and just do this thought experiment with me. And I want you to look at, I want you to remember what I said earlier in the lecture. So there's 2,000 stars you can see with your naked eye. We don't have telescopes left yet or anything, all right? And now I want you to imagine, you can think of them as data points. Imagine you're doing a project, right? So you're tracking the movement of every dot in the sky. So there's about 2,005 of these, all right? So 2,000 of them all behave perfectly, and I mean really well, with your model that they rotate around the Earth. But 5 of them don't. So these 5 objects got special names and were called planets, because the planets didn't behave like the stars. Now, maybe I won't make you be brave and admit it and put it on record, but I want you to think, if you had 2,005 data points and a theory by which they behave, and 2,000 fit perfectly and 5 didn't, I think most of you would throw out the 5. I'd probably throw out the 5, right? There's no reason to think that those 5 will matter. But in this case, they do. This is a good reason also not to, not to throw out the 5. But we want to understand, well, what do you mean they didn't behave? So if you recall, the stars, let me go back to I just need to go here for a minute. Sharing files. That's what's next. I want to show one of those pictures right here. All 5,000 of those points, those stars, move in these concentric circles. And as you saw, we could tell true north from the smallest concentric circle. However, the planets, when they move, they move according to this very strange motion, which we call retrograde motion. You might have heard that term in a popular topic in which stars are used to tell fortunes that we won't really talk about much in this class. But retrograde is when you'll notice the planet is moving just in the night sky, and then it goes backwards, changes direction again in this loop, and then moves forward. And this is called retrograde motion. So this did not follow a circular motion and caused some concern. But again, only 5 points did this, and there was no explanation. Now, there was one way to fix the retrograde motion, okay? The way to fix the retrograde motion was to put the sun at the center of the solar system. And you might be thinking, well, duh, why not? And let's see what happens when you do that. If the sun is at the center of the solar system, and we're orbiting the sun, retrograde motion can just be explained by the Earth orbiting faster than Mars, right? Because you'll notice if Mars is just chugging along and the Earth is moving faster, it will approach it and then move away from it, and everything is described. So you might be saying, well, okay, why isn't the sun clearly at the center of the orbit? Because now, remember, we don't have modern technology in this thought experiment. We only have our eyes. Our eyes make all the other 2,000 points problematic now. And let's get an idea for how that happens. With your eye, what you expect to see if the Earth rotates around is this idea of stellar parallax. Now, if you're struggling to do this, the best way to see what this parallax is to put your finger in front of your eye by your nose and close one of your eyes and go back and forth. What do you see your finger doing as you go from 1 to 2, 1 to 2? You see I'm blinking here, I'm going back and forth? What do you see with your finger? Someone chime in. All right. Right, you see it in different angles, but it's moving right back and forth, right? It looks like its position is changing. Now, get your finger, do the same thing, but move your hand farther away. Is it changing angle by a bigger angle or a smaller angle? Right, it feels like it's moving. Good, it's a smaller angle. So the idea here is that if we do, you can think of this as July as your left eye open and January as your right eye open. And basically they would expect that there should be this parallax effect in the stars that we should see every 6 months. That would be the prediction. Here's the problem. With our naked eye, we don't observe stellar parallax. Okay? So now, with that in mind, with that in mind, we couldn't, it was either one model with the Earth at the center with 5 points that don't work right, or we can resolve what's wrong with those 5 points, right? And we can put the center, the sun at the center, but then we have a problem with the other 2,000 points. And I think it's fair to say that all of us would pick a model with 5 points that don't make sense rather than the other 2,000. So that's where you get a geocentric model of the Earth. Now, as better tools come along, like the telescope, that is going to give us more evidence, right, to dismiss or to overrule or overturn or falsify, that word I used last week, falsify the geocentric model. And we're going to start to understand that process as we talk about the next, as we go through the next chapter and discuss observations in a more rigorous manner. Right now, these are just colloquial observations. We're going to focus more into how specific observations could be used with a little more detail, and then we'll get to astronomy, or at least the telescope. Okay. So so the parallax could mean one of two things: that the stars were so far away that stellar parallax is too small to notice with the naked eye. This seemed unreasonable because we could see the light. It didn't make sense that the light could be so far away that we could see it, but not see the parallax. Like, why would you be able to see it? Or the Earth does not orbit the sun, it's the center of the universe. So again, they couldn't conceptualize the stars being that far away. Again, it didn't make sense that you could see something, right, but it would behave in ways different than everything else you could see. That's actually understandable. Then the way they make it see here, they make it seem like they're dumb, but they're not. They're just limited by by the conclusions they can draw. But the stage was set for this battle between Earth-centered and Sun-centered models, with Sun-centered sort of being suggested just to solve this retrograde problem and seeing if they could figure out something else. But most people not wanting to throw away the other 2,000 points for the 5 points. Okay, so let's get to the next chapter. We are ready to move on. So we'll take our break around 5, just so you know. So we want to share files. We will stop sharing that, and we will start sharing chapter 3. All right, if it clicks to chapter 2, I'm going to be upset. Okay, this is getting better. All right. So we want to now that we can see what we observe, we want to start putting structure to the observations, otherwise known as science. Now, I don't remember if I talked about the nature of science. It's not a bad topic to bring up almost every lecture, though. Basically, science is a way of arriving at certain conclusions with a certain set of rules. It's restrictive, but precise, which means the questions it answers, it can answer well. But there's this need I've noticed when I watch, even in the coronavirus pandemic, you can sort of see the difference between a scientific approach and a non-scientific approach. So if you watch press releases and you watch Dr. Fauci talk about the virus and the spread, he's very scientific. But you'll notice when you watch anyone else talk about it, that's not a doctor, whether it's a politician or a pundit, they want to sound hopeful and encouraging and things like this, and they mention something's happened and then we'll draw a conclusion about it. I think the president has, for example, mentioned mentioned a antiviral that's being developed and was very excited about it and very hopeful. And while his conclusion was not scientific, it may be, whatever your feelings on him, it may be too harsh to judge him for being human, right? The response is sort of human, particularly in a place where people are kind of scared. But it's not scientific. And when you listen to Dr. Fauci talk about it, again, you notice he's not the lack of excitement is missing, hopefulness is missing. He talks about the context of the data and the fact that in order to draw the conclusions aren't ready to be drawn in a scientific manner yet. Dr. Fauci is a very informative person, but he's not really super exciting and thrilling, right? You're not voting for Dr. Fauci as class president, probably. He's not uncharismatic, but he's not the most exciting speaker you've ever heard in your life. It's probably closer to listening to me. Which I fully admit I'm not the most exciting person you've heard. Maybe today to break up the day, but I want you you can even go back and listen to Trump's response has been typically panned, but to keep this from devolving politically, Mike Pence's responses have been seen as pretty good, or at least presidential, if you will. So if you want to look at Republican, you can look at what Mike Pence says about the measured approach Mike Pence takes and that Andrew Cuomo take, and you can see them talk about the disease, and even still they talk about it in terms of emotion and fear, and they defer to the CDC, but you should compare both of those to how Dr. Fauci talks about them. It's really quite interesting and makes my point within a current event. And you'll see that when we talk about, but what I want to sort of emphasize is to look at this from the other way. There's this desire that science can answer everything and is actually the structure from which to explain all of life. Science can, like I said, science explains what it does very well. And there are things that you should understand scientifically, absolutely. And you should have some literacy about science, but understanding what science can explain is also important to understanding what science can't explain, right? So for instance, I'm your physics professor, your astronomy professor, and I can sit here and tell you with all my professorial authority that, prime rib is the best cut of steak. I say it, therefore it's true. But that's not a scientific fact. I mean, I think it is. No, I'm just kidding. I mean, it's but it's an opinion, right? It's an opinion that has meaning for me. And you have opinions or thoughts or even things that are facts for you, like how you feel about your parents or your siblings, your friends, that science doesn't really have a say on, right? So if you're going to ask a scientific question, or if a scientific question is going to be posed, it has to be falsifiable. And what I mean by that is it has to be, you have to be able to propose an experiment that falsifies the conclusion. right? You can have all sorts of cool thoughts, but if there's no experiment to test the cool thought, it's not science. It can sound technical, but it's not science. And science has had some pretty amazing wins. I mean, we have the development of the germ theory, which has helped us create a response to the coronavirus. I can't say how deadly it will be, but I think we will be better off than the Spanish flu of 1918. If you look at that, that was an H1N1 flu outbreak, and basically it infected, some estimates have it that infected 33% of the world's population at the time, and it killed over 50 million people. So it's our understanding of germs and germ theory that helps us have a response and not have something like today, this coronavirus, sweep through and run out of doctors. And if you look at plagues, that's actually interesting. What happens is people start dying when we run out of doctors. So that's why that's something to keep in mind. That's the real tipping point. When you run out of doctors to care or equipment, that's when things start to really, that's when things go bad. So that being said, we're going to look at the first developments of scientific measurements that were predictive, and a lot of things used to make these predictions were the stars or astronomical events. So let's go and see some. So astronomy is the oldest of the sciences, and again, practical predictions. Oh, you can't. Can you see my pointer here? Yeah, practical predictions led to it being developed, right? The more practical your predictions can be, the more interested people are in them. So let's go. Ancient people in Central Africa could predict seasons from these tilts of the moon, right? So from the orientation of the moon, they could see that it sort of rocked back and forth between January and December, and that the tilt was greater. You know, they could see that this part of the tilt would be greater during the rainy season than the dry season. And again, predicting rainy and dry seasons when you're trying to farm is critically important. Okay? So you'll notice that our days of the week were named. We have 7 days of the week because in addition to our 5 planets, we have the moon and the sun, right? That's 7 objects that aren't stars. So we name our 7 days Sunday. If you go between Germanic, English, French, and Spanish in Western culture, they're named after these. If you combine at least those ways of looking at things, you can see the derivative of the names. So you'll notice that Sunday comes from sun, from English. Germanic and English really should be the same because they're kind of similar languages. The moon, Monday, right? Mars, you'll notice, comes from more Latin, Marti, Martes, from Spanish and French. Mercury, again, has more of a Latin influence, Spanish or French. Jupiter, again, Spanish or French. But you'll notice things like Friday, Freya, and Thursday, the names actually come from the Germanic gods, right? And Wednesday. So you can see the object. This is what it is in English. The English day associated with it, and it's, if you combine these, Venus, Freya, Friday, Mars, Marty, but 2, so that's where we get Tuesday. So a lot of it comes from these 4 that we have come from Germany, and then Sunday and then Saturday. They come, even though they sound different, they all sort of come in the same way. Okay, and they're all named after the same objects. They go hand in hand. So that's a main pattern we've come up with. So daily timekeeping, tracking the seasons and the calendar, monitoring lunar cycles, monitoring the planets and the stars. You could predict eclipses, and much like Bed Bath & Beyond, there is more. And of course, the more section is not well defined. We want to see now, we want to get an idea of how, of some of the items and how that were used to take these observations. So you'll notice this is an obelisk. This was probably stolen from Egypt and moved to Italy, as most obelisks were. But you can see the shadow it creates, and the movement of the shadow can help you keep track of daily time. All right. Stonehenge was. Oh, hold on. I need to put that. And hold on. Sorry, the microphone. Let me put these away. Hold on. Well, I'll need this one still to silence. I told her I was teaching. Parents never listen. Anyway, so where were we? So Stonehenge. Yeah. No, I know. We have to make class a little fun, right? There has to be some chaos, otherwise, no one. Yeah. Anyhow, Stonehenge. Stonehenge was completed around 1550 BC and is thought to act as a calendar. Okay. Stupid computer. I don't need those. And is thought to act as a calendar. It can align with several astronomical events. We have a model of the Templo Mayor in Mexico, and the top of it, I believe, aligned with solstices, and you could see, you can predict the seasons. We have in New Mexico, on Sazi Kiva, aligned north and south, and in the southwest United States, a sun dagger marks the summer solstice. So you'll notice there's things to mark solstices. The shortest day and the longest day would be important, right? Particularly when your survival was determined of knowing when these would happen. This 4,000-year-old structure in Scotland shows the moon in this exact position every 18.6 years. So this is a sort of a Stonehenge-like structure, but it's not clear that it serves the same purpose. And again, as they find more about Stonehenge, there's more to it. In Peru, it says that these lines and patterns are aligned with stars, but it's a bird. Someone was drawing a bird. If you look, they were using the patterns of the sky, of the stars, to point each part of the bird as ways to connect straight lines. I think it's pretty obvious here. I think people are making way too big of something. At least when I see.
It looks like a hummingbird, to be honest.
Yeah, it looks like a bird, right? It's a bird.
Yeah.
It was no idea. It was not aliens. If you look, it's too imperfect. It looks like someone trying to draw a big picture, and they use the stars as a guide. So I mean and I agree with the hummingbird part. It's the pattern is there. So I'm not sure why this is looked at as mysterious, but not all aliens are great artists. That's a fair point. We can talk about aliens at some other point, though we may get there. Who knows? I don't talk about aliens as much as the life in the universe does, so don't get too excited. I think you'll be disappointed in my alien stance. It's not that exciting. But usually people want to talk about them when we see just how many stars are out there and how many planets are out there. But Machu Picchu in Peru, the structures are also aligned with solstices. So you can see throughout the world that aligning these structures with solstices was a big deal. This is also a nice picture because there are people there. I always thought this was an empty day there. But what do you know? You can see, I've never seen it at this high resolution this close before. There are definitely people there. I've always wanted to go there. In the South Pacific, the Polynesians were very skilled in the art of celestial navigation. So the Polynesian islands are very cool if you like Lost. It's basically where they are. There's an island, very large chain of islands. The islands of Hawaii are thought to be sort of the edge of the Polynesian islands, and they go all the way down to like Samoa and by Australia and Southeast Asia. I mean, it's a large geographical area. It's just mostly water. But getting from island to island was important, and using the sky to navigate could tell you where you were going. So night could sometimes be easier to navigate than during the day. So that probably gave rise to the first night shift crew as well. So observations. Now I usually skip this one. This is a lot of guesswork. Cave paintings from 18,000 BC may suggest knowledge of lunar phases. It looks like a horse. It might be a horse, and it might be spitting, and it just this is a real reach. I'm not going to teach this as look what they might have seen. It could be possible. I don't see it. Obviously, people 18,000 years ago or 20,000 years ago that would have existed, because we know people were there, would have been known about lunar phases because you could just look up and see them. They might not have known why they occurred. That's true, but all you have to do is one of these. Oh, it changes the next night. You know, you get the idea. Probably start wondering about it. So, let's see here. Now, in 1400 BC, Chinese scholars very clearly recorded a supernova that we can actually look at the remnants of and get right back to the seventh day of what is essentially the seventh day of the month. A big new star appeared and then dwindled, and we can see that in 1400 BC, which would be 3,400 years ago. Some things to understand is looking at the stars and making conclusions and learning about the universe is something people all over the world did. It's not a centralized, it's not something that was born in one part of the world. You might be able to make the argument that the telescope and thus sort of more, our modern sort of structure of physics came from Newton and Galileo, but they built on information from all over the world and contributed to understanding information all over the world and have since gone all over the world. Physics is a study that is done in every country, and there are collaborations between nearly every country in the world on the biggest projects in the world. So it's a global effort of people, and it's kind of cool in that way. But they use all these observations were made to make predictions, right? Where am I going? Should I plant a crop? What time, how long will this process take? These are the kind of questions you could do over and over and over again that you would see, sorry about that, that you would see, you would start to, want to refine and make better. And this brings us to how science is used, or this idea of repetitively doing something to get better information has been used throughout people all over the world. So science is a human endeavor, not a African endeavor or simply a European endeavor or an American endeavor or a Chinese endeavor or a Brazilian endeavor. It is a global endeavor. Yeah, I put in another throat lozenge. Yeah, sorry about that. It's been a rough 2 weeks. So, and ginger tea, it's a complicated situation. My apartment has, how shall I say, limited resources. Oh, I get the Rapolas, and I'm currently eating the naturally soothing. Oh no, that's not the honey herb. So it's ginger. It's the closest I'm going to get to ginger tea.
Rapola.
Huh? Oh, nice. Well done. but yeah. I'm actually running out. I probably need to see if I can forage out and get more, but maybe tomorrow when it's not raining. I don't know if it's raining in New York. It's certainly crappy here in New Jersey. I'm gonna tell you that. So let's go forward into our next section. Okay. So we want to sort of focus on the ancient Greeks. One thing the ancient Greeks did do that they deserve a lot of credit for, and I keep saying this, and I've not heard more than open it to it not being true, but it seems to be the case, that the ancient Greeks were unique in coming up with a system, a descriptive system of the universe that did not defer to the supernatural. Now, of course, the Greeks had their system of gods, but what we call natural philosophy or modern science traces its roots to 3 specific Greeks, not a bunch of gods. And their goal was to eliminate the supernatural from descriptions, from understanding the world through what they call natural processes, meaning something that's measurable. So let's take a look at what they did. Now, the mathematical and scientific heritage that we have did originate in the Middle East. Okay. However, that's the measurement themselves, and these had influences through Asia to Europe and to Africa. All right, but the structure of philosophy, of natural philosophy, that started here in Greece. All right, so basically, I thought they would go over what the. Okay, so we're not going to do that. So basically, if you study philosophy at all, this idea of natural philosophy, what the Greeks did, insisted on, hold on, let me just, I'm finding this a little perturbing. All right, so that's where we come in with the Greeks. Okay. Now, wait a minute. All right. Okay. So before we get to the Greeks, let's get there. Around Greece, you'll notice in the old map. Sorry, I just got a little flub. The order wasn't making sense. So you'll notice that Greece is very close to ancient Egypt and to Mesopotamia, all right, and to the Middle East, to Babylon and Persia, okay? And what you'll notice is that as knowledge flows throughout from the mathematical origins in the Middle East through Greece and Egypt, those were also known as centers of learning in the ancient world, all right? So you have the ancient library of Alexandria, was thought to be the largest library in the world, and when it burnt down, it was whatchamacallit, a lot of human knowledge was lost. The way to think of it as this way is what a precarious position it was. Imagine there was only one copy of Wikipedia, and to go to it, you had to go to this Library of Alexandria, and that was it. You couldn't access it on your phone, couldn't get to it any other way, and all the knowledge, basic knowledge, and then all the journals and everything, that the follow-up sources were all in the same one building. That building burns down, you're in trouble, and that's what happened. I believe, I've heard, I don't know if it's true, I believe that like if you came to Alexandria with a book, you were required to submit the book to the library so that they could copy it, and then they would give you the book back. So they were very serious about this knowledge. Now, the Greeks, why does modern science have its roots with these Greeks? Well, the Greeks were the first to make models. Again, they tried to explain patterns in nature without resorting to myth or the supernatural, right? And again, this isn't all Greeks, but this is your Socrates, Plato, and Aristotle, right? Your Greek philosophy, or They usually call it Hellenistic thinking, is what it's called historically. So in that sense, they did that, and this was a unique way of thinking for the time. Now, the underpinnings of the Greek model were geocentric. Again, right? We talked about data points, so we have Plato and Aristotle. So ideas they had were that the Earth was to be at the center, and the heavens must be perfect. Now, what does perfect mean? Objects move in perfect spheres or in perfect circles. This idea of perfection and absolutes permeated these particular philosophies. What is absolute truth? How do I make a position that is absolutely true? Modern science doesn't really do that. Modern science analyzes data and comes up with conclusions within errors. And one way to win a Nobel Prize is to come up with a substantial decrease in the error bars. But even the most fundamental branches of science indicate that the error bars must exist. So it's even though modern science traces its roots back to this Greek way of making models and thinking, there's a lot that we just disregarded. There was a shift from a philosophical approach to what we call physics. And that started with Newton. But Newton would have described himself as a natural philosopher. So going back, they were able to use their observations to make some pretty spectacular predictions. So remember I told you about the Earth being, the circumference of the Earth not only being known that the Earth was round, but that it was, they knew how much round it was. So if we look here, in 240 BC, Aristophanes, I don't know, I messed that up, will measure the Earth, all right? And so basically, he'll go from two places, right? So from Siena to Alexandria, right? And he'll use those sundials and things to look at the position of the sun and get this, that there's this 7-degree, this curvature arc, right? That they'll be able to measure this 7 degrees pretty precisely. And from that 7 degrees, all he has to do is figure out how far he walked. So he was able to measure the distance at about 5,000 stadia, all right? So stadia is an ancient unit of measurement. Now what he found is that using the sphere, if the Earth is a sphere, it should have a radius of 250,000 stadia. Now the Greek stadium was approximately equal to 1/6 of a kilometer. So 250,000 stadia would equal 42,000 kilometers. Now compare that with the modern value we have with all our lasers and other things. So I shouldn't put quotes in lasers. I was quoting a movie there. Lasers are a real thing that we use to figure out this stuff. But our satellite imaging and all our modern technology, we can directly measure the circumference of the Earth at 40,100. So 2,000 years ago, or 2,200 years ago, that's not bad, right? Between 42,000 and 40,000, you'll find that it's within 5%, which is, good enough for government work. We'll take 5%. Now, even though they had models, the models could not explain, if you remember from last chapter, this epicycle motion. Okay? Just couldn't do it. So, over a period of 10 weeks, you'll notice, we can see 1, 2, 3, 4, 5, 6, 7. Mars stops, moves backwards, and then moves forward again. So that's again this retrograde motion. They were sometimes called epicycles to explain these epicirculars. So what the Greeks tried to do is include in their models these retrograde or epicycle loops. All right, these weird things. But let's. It's 4:58. So let's take our break. Let's come back at. I'm going to stay in the room. I'll probably disable my video, but leave my audio on. So if you want to chat, I'd say don't be too far away. So let's say at about 5:30, we'll come back and we'll start. Yes, so I'm recording the lectures. So everything we've talked about and seen, It'll take a while for it to process, but once it's processed, it should go on. It should go on the site. And I'm going to record instructions later tonight how to do that when yours come. I'll see if I can stop the recording now. It should process the first one. So I'll